This is the first video in a chapter on electronic structure and periodic properties. We're going to start by talking about the limits of classical mechanics and what that can tell us about light and the nature of energy. We're going to talk about wave properties of light, particle properties of light, and the new and improved Bohr model of the atom. So in the previous video, we focused on atoms. So now that we know about atoms and the subatomic particles inside of them, subatomic particles, we're going to focus in on one type of subatomic particle, the electron, in this chapter. Because electrons are the reason that bonds and reaction between atoms and molecules happen. But before we can start with that, we need to take a step back. There's some information we need first. So to understand electrons and how they're organized inside of an atom, we need to take a step back and talk about the nature of light. We need to first understand the nature of light. And I promise this will make sense very soon why we're talking about this. So we need to talk about light. And to talk about light, we need to talk about waves, because light behaves like a wave. So light, which is also called electromagnetic radiation, is its fancy name for all types of light. Doesn't quite fit on the page. There we go. Also called energy. Acts like a wave. And waves are things we've seen before. We're familiar with them. There are sound waves. There are waves in the ocean. There are waves that you do when you're at the football game and people make a human wave. We sort of fundamentally understand how waves work. So I'm just going to draw a picture of a wave, and then we're going to label the different parts. So you have the terminology ready to describe the anatomy of a wave. And then we're going to draw a smaller wave over here. Okay, so there are a couple of different properties of waves that you need to be able to define. So the first one is the amplitude. And the amplitude is half of the distance from the top to the bottom of a wave. So usually we draw it as the distance from the top to the center line, and it should be equal to the distance from the bottom to the center line. We can measure the wavelength. So amplitude is from top to bottom. Wavelength is from one spot in the wave to that same spot in the next cycle. So I like to draw it from the bottom of one wave to the bottom of the next cycle. That's called the wavelength. And we're going to have a symbol for wavelength. The symbol for amplitude is an A. The symbol for wavelength is a Greek letter called lambda. That is what has traditionally been used for it. This is a lowercase lambda, looks kind of like an upside down Y. And then something that's sort of complementary to wavelength is the frequency. And frequency is the number of waves that pass this point per second. So the symbol for frequency is another Greek letter. It looks kind of like a cursive letter V, and it's called nu. So there are three properties of a wave already: frequency, wavelength, and amplitude. And frequency and wavelength are related. They are inversely proportional. So we can write that like this. Frequency is proportional to 1 over the wavelength. And what that means is, as the frequency increases, the wavelength will decrease. Or as the frequency decreases, the wavelength will increase. They are going to change together in opposite directions. Here we have a second wave over here. We can go ahead and mark those same features on that one. So the amplitude, the distance from the middle to the top, is here. And if we compare these two, we can say that the amplitude of the red wave is smaller than the amplitude of the green wave. Amplitude is smaller. We can mark in the wavelength. And we don't have two bottoms of the wave here, but we do have this middle point. So the wavelength is this entire length here. There's the wavelength, and if we compare the wavelength of the red line to the wavelength of the green line, the wavelength of the red line was drawn to be longer or larger. And since wavelength and frequency are inversely proportional, if the wavelength is going to be larger, then we know the frequency for this wave will be lower or smaller. Okay, so we should be able to recognize those different parts of the wave. And back here, we said that light is also called electromagnetic radiation, and that is because technically the word light only means visible light that human eyeballs can see. If we want to talk about all the other different wavelengths or frequencies of energy, we call it electromagnetic radiation. So let's put in a note about that here. So there is a huge range of wavelengths / frequencies of light. Wavelength and frequency are kind of just two different ways to measure a wave, like two different kinds of measuring tape. So we call all the different ranges of light the electromagnetic spectrum, because it's a spectrum of electromagnetic radiation. If you want to learn more about that, see physics. And so we'll talk about all the different kinds of light here. So the highest energy form of light is gamma rays. Then we have X-rays is the next portion of frequencies. We have ultraviolet light. That's supposed to be an L. You get the picture. Next, we have visible light, the kind that humans can see. Very exciting. Infrared light, energy that makes you feel warm. Microwaves, like you use to heat your food. And radio waves at the low end. With FM waves coming first, and then AM waves. So this is a spectrum. It's a spectrum of light, and we can show the frequency and the wavelength of the different parts of the spectrum. So this end over here, the gamma ray end, this is going to be the high frequency end. Also the high energy end, which we'll talk about later. And the short wavelength end. So the gamma rays are the shortest and the smallest. They are about 1 millimeter in wavelength, very, very short. And over here at the radio waves end, this is the long waves. Radio waves are about the size of a car. They're very big. And they are low frequency, low energy at this end. So if we were to draw, sort of like indicate the wavelength here at the gamma ray end, the wavelength would be very, very short. It would start to get a little bit longer through X-rays and ultraviolet and visible, and longer and longer and longer and longer, all the way to radio waves. So the gamma rays have the highest energy and the shortest wavelength. And as we move through the spectrum, the wavelength gets longer and longer, and the energy gets lower and lower. And this part of the spectrum in particular, the short wavelength end, that's the high energy end, that's the dangerous ionizing types of radiation you don't want to come into contact with. And this part of the spectrum is the only type of light that human eyes can see. So visible light that we can see is only one small type of energy out of all the different range of energy waves that we could have.